Hello, my name is Deborah Adams and I would like to welcome you to today's webinar from the IEA Clean Coal Centre. My colleague Kyle Nicol will present on recent developments in particulate control. Kyle has just completed a report on the subject which will be available next week to download from our website. Reports can be downloaded free of charge by residents of member countries or employees of sponsoring organisations after a one-off registration. Visit our website for more details. Also, if you have any questions during the webinar or indeed any comments, please click the question button at the top of your screen, type the question in, and Kyle will answer them at the end, or you can contact him after the webinar. Okay, I'll now pass you over to Kyle Nicol.
Hello, my name is Kyle Nicol and I will review the recent developments in particulate control. This webinar is based on my report of the same title. I will start with an introduction, move on to electrostatic precipitators, then fabric filters, then hybrid systems, and then I'll summarise. The top left picture shows fly ash being emitted from the stacks of coal-fired power plant. Fly ash is made up of particulates. The top right picture shows particulates close up. Fly ash particulates are an agglomeration of molecules, predominantly silicon dioxide, aluminium dioxide, iron oxide, calcium oxide, unburned carbon, and to a lesser extent trace elements, including toxic metals such as mercury. Airborne particulate matter can cause adverse health effects on the public. The bottom left-hand picture shows recent air pollution in Shanghai. Fly ash emissions from coal-fired power plant are limited to a specific value, known as an emission limit value, which has led to the installation of particulate control. This table shows current emission limit values in some countries. Increasing concern on public health has led to more stringent emission limit values, which have been met mainly through enhancing existing particulate control. The reference to ICSC power plant shows that emissions of particulates can drop to 1 milligram per metre cubed with modern equipment and good quality coal. However, enhancing particulate control is made difficult because coal-fired power plants are progressively operated outside of design conditions. Firstly, fly ash properties are altered due to firing different fuels and the retrofit of emission reduction technologies. Secondly, coal-fired power plants are designed for continuous operation, have been operated in cyclic operation. And finally, space restrictions on site limit what work can be done. Despite this, lower emission limit values have been met with additional benefits. Fortunately, the addition of wet flue gas desulfurization downstream of the particulate control also scrubs out, on average, 60% of the particulates from the ESP outlet. This figure has been seen to be 73.5% in China. In coal-fired power plant, electrostatic precipitators make up roughly 80 to 90% of the particulate control fleet. Conventionally, flue gas exits the air heater and passes into a cold side ESP at around 130 to 180 degrees Celsius. Wide discharge electrodes negatively charge particulates into ions. Electrostatic attraction causes these ions to migrate to and accumulate on the plate electrodes. The particulates therefore become part of an electrical circuit. The same principle is seen on your TV screen or computer screen as it gets dusty. In dry ESP, the accumulated particulates are periodically knocked from the plate electrodes by wrappers and fall into hoppers. Particulates must be able to hold sufficient charge. The ability of a particulate to hold charge is determined by its resistivity. Fly ash with low resistivity does not accumulate on the collection plates. Fly ash with high resistivity causes electrons to flow to the discharge electrode in a process known as sparking, which significantly reduces collection efficiency. Like most equipment, ESP needs maintaining. Worn electrodes and wrappers should be replaced or upgraded. The plate electrodes can be modified in two other ways. Firstly, by increasing the spacing between the plate electrodes, and secondly, by increasing the width and the height of the plate electrodes, providing there is sufficient space in the casing. Air leakage should also be minimized. Non-uniform flow will lower collection efficiency and increase power consumption. Flow control devices are added to the ESP to ensure flow distribution. The size, type and positioning of flow control devices have historically been determined using physical models and in situ field tests, which are expensive and time consuming. However, the last decade has seen computational fluid dynamics driven by computers revolutionise the way in which fluid flows are analysed. CFD analysis can be used to quickly and cheaply identify the most effective use of flow control devices. Many companies provide services for CFD analysis. One example from Stieg Energy Services shows a 15% drop in average ESP outlet emissions. The advent of miniature and affordable electronics have revolutionised ESP power supply and control. New switch mode power supplies charge particulates more effectively, and microprocessor-based control optimises operation. The results are improved collection efficiency and decreased parasitic load. The work simply involves replacing the ESP power supply. This will entail a short unit outage and a precise and low capital cost. Waigaoqiao Power Plant in China recently installed switch mode power supply and microprocessor-based control. The ESP outlet emissions dropped by 52% and the auxiliary load dropped by 69.5%. A dramatic option is to remove all the ESP internals, replacing or upgrading everything apart from the existing casing and hoppers. In 2006, ICSC coal-fired power plant rebuilt an ESP. The following enhancements were made: increased width and height of plate electrode, increased spacing between the plate electrodes, minimised the air leakage from 5 to 3%, upgraded all wrappers and discharge electrodes, modified flow control devices using CFD analysis, and finally, 2 more fields were added to the existing 3. After a year of operation, emissions reduced from 265 to 31.5 milligrams per metre cubed, a decrease of 88%. A statistical research project in China has shown that it is technically and economically viable to adapt 86% of the installed ESP fleet to meet the emission limit value of 30 milligrams per metre cubed. The single most important enhancement would be an additional collecting field. Fly ash resistivity becomes too high when there is a switch from firing low sulfur coal to firing low sulfur coal. However, fly ash resistivity can be decreased by adding chemicals into the flue gas in a process known as flue gas conditioning. A moderate capital cost and a short unit outage are required to install the injection equipment, and an additional operating and maintenance cost will be incurred. In 2012, an FGD system using sulfur trioxide was installed on Guangdong Pinghai Power Plant in China. This succeeded in meeting an emission limit value of less than 45 milligrams per meter cubed, with efficiencies peaking at 99.65%. For an improvement in collection efficiency, along with other advantages, the listed variations of ESP technology could prove suitable. These variations can be retrofitted to the existing ESP or built as an additional polishing device. In both cases, large capital costs and long outages are required. However, more operating experience is needed to prove the newer technologies. Coldicide ESP operates in a temperature range of 90 to 100 degrees Celsius, as opposed to the conventional 130 to 180 degrees Celsius. Advantages include increased collecting area, decreased fly ash resistivity, and decreased parasitic load. Disadvantages include increased fouling and corrosion. Alstom installed coal-side ESP on Tosho Nanyo coal-fired power plant in Japan. Results were positive and the lowest emissions were 6.7 milligrams per meter cubed. There was also a 50% reduction in parasitic load. Since the 1990s, Mitsubishi Heavy Industries have installed Coldicide ESP on over 10 gigawatt of Japanese coal-fired power plant. Moving electrode ESP is designed for applications where the accumulated fly ash cannot be effectively knocked off via conventional wrapping. Instead, it is brushed off. The moving parts will wear with high fly ash loading, so MEP is presently installed in the last one or two fields of an ESP. MEP requires half the space of conventional fixed plate ESP, and in 2011 there were 30 MEP installations in Japan. Instead of wrapping, wet ESP washes away accumulated particulates with a water spray. This requires a complex water delivery system and cleaning system. Wet ESP has high collection efficiencies of aerosols and all particulates, and can condense water vapour, leaving a plume-free stack emission. Historically, wet ESP has not been used on large-scale coal-fired power plant. However, it could have favourable economics at small scale, or when used as a polishing device. Recently, wet ESP has been incorporated into wet scrubbers in order to create multi-pollutant control. Cross-flow ESP simply illustrates that the Developed by Few and Longking, the electromechanical double zone ESP separates the charging zone from the collecting zone. Both zones have separate power source running an 80 kilovolt DC power supply. This technology has high collection efficiencies of all resistivity fly ash. Recent installations in China have shown an outstanding performance of 99.96 collection efficiency. In 2011, there were 74 operational units in China. Cross-flow ESP simply illustrates that the conceptual development of ESP is ongoing. Fabric filters collect particulates by passing flue gas through a filter which the particulates are caught on. A common example is a vacuum cleaner. Fabric filters have the highest collection efficiency of all particulate control, including PM2.5. Unfortunately, forcing the flue gas through filter bags causes a substantial pressure drop, which requires a high power induced draft fan. Fabric filters have to be well maintained and operated, otherwise pressure drops can get too high, which will result in filter breakages. Fabric filters are predominantly cleaned with a pulse jet method. This involves pulsing individual bags with compressed air to dislodge the filter cake, which subsequently falls into hoppers below. The filter will depend on the level of fly ash removal required and the operating environment with regards to chemical degradation, thermal deterioration and mechanical wear. This table summarises the fabric types. Generally, better performance will be seen from more expensive fabrics. Various surface treatments and coatings can be implemented on the fabric for different performances. For example, a PTFE coating will increase filter cake release. This table summarises the treatment and coatings. PPS felt laminated with an ePTFE membrane has proven to make an effective and reliable filter and has been used with modern pulse jet fabric filters. Microprocessor-based control optimizes operation, the main parameter being the cleaning cycle. Pressure sensors across the filter bags indicate when the bags need to be cleaned. Cleaning should only be carried out when necessary in order to prolong lifetime and gain maximum collection efficiency. Sequential cleaning has to be avoided as it simply leads to re-entrainment to cleaned bags close by. A random order will help gain best performance. In much the same way as with ESP, uniform flow distribution in fabric filters can be ensured using computer-driven CFD analysis. This will allow maximum collection efficiency with prolonged filter bag life. Sorbents can be injected upstream of the fabric filter for capture of other pollutants in the filter cake. A proven and effective sorbent is activated carbon for capture of mercury. Unfortunately, the fly ash will be contaminated with sorbents and pollutants and potentially cannot be sold to the construction industry and may even incur disposal costs. The work involves a moderate capital cost, a short unit outage with increased operating and maintenance costs. ESP and fabric filters have advantages and disadvantages, which have led to the development of new hybrid systems which aim to exploit the advantages of both, such as low pressure drop and low cost of an ESP combined with high collection efficiency, including PM 2.5, and multi-pollutant capture capability of a fabric filter. EPRI in the USA have developed the following hybrid systems: Copac and Toxicon. Copac places a fabric filter downstream of an existing ESP, acting as a small polishing device. Copac is operational on 2 units of the EC gas and coal-fired power plant in the USA. After a decade of operation, Copac has proven to halve stack emissions, allow plant flexibility, and has made the FGC system redundant. Toxicon is Copac coupled with sorbent injection upstream of the fabric filter for multi-pollutant control. This arrangement leaves only 1% of the fly ash contaminated with sorbents and pollutants. Toxicon was successfully demonstrated at a small scale on a coal-fired power plant in the USA. Fugue and Lonking have developed the electrostatic fabric integrated collector. This device consists of one ESP field to capture the bulk of particulates, followed by a pulse jet fabric filter to capture the remainder. EFIC has shown a 99.8% collection efficiency on a power plant in China, and in 2012 there were 87 operational units in Asia. This table summarises the pros and cons of particulate control. Generally speaking, cold side, dry ESP still dominate the market for particulate control. Fabric filters and hybrid systems are becoming more popular, and wet ESP and fabric filters are evolving into multi-pollutant control. There is no silver bullet for particulate control, as individual coal-fired power plant vary in aspects such as fly ash properties, emission limit values, space availability and labour cost. However, providing correct assessment is undertaken, there will be an effective option applicable at any site. Now that's all done and dusted, I would appreciate if you could rate this webinar via the rate button at the top of the page. And now the panel is open to any questions.
Thank you very much, Carl. We'll now click on the question button and we'll see what questions have come in so far. Okay, there's one question at the moment. Carl, the question is, I operate a coal-fired power plant which has an old underperforming ESP. What would you do to lower particulate emissions?
Well, if there was space on site, I would rebuild the existing ESP and add another one or two fields. However, if there wasn't any space, I would install a hybrid system such as the one developed by Untitled.
Thank you very much for your answer. We'll just give you a minute to see if any more questions come in. While we wait, I'd just like to let you know that Carl's PowerPoint presentation will be available to download from our webinar page on our website later on today. And the next webinar will take place on Wednesday the 22nd of May at midday UK time. Our colleague Dr. Chen Zhu will give a presentation on her latest report, which has been very well received. Her subject will be developments in circulating fluidized bed combustion. Okay, there have been no more questions. If you do think of any... Oh, hang on, one more. Over to you, Kyle. The question is, are high-temperature ceramic baghouses appropriate technology?
My report briefly covers ceramic baghouses. However, there's been no substantial recent developments.
And the last question has just arrived from Peter, who asks, what are the differences in the lifetime capacity factor of ESPs and fabric filters?
ESP can last indefinitely, provided that they are maintained well. They can consistently be upgraded, and there's ESP that are performing with high particulate capture up to 40 years old. Fabric filters, the actual bags themselves need replacing frequently, depending on the corrosion and wear conditions. That's it really. Thank you.
Thank you, Kyle. One more question has arrived, which is, in EFIC, what is the size of the ESP field and PJFF sections? A lot of acronyms in that one.
I'm not entirely sure what the size is, but there are specifications on the Untitled website. There's only one ESP field, and there are 3 fabric filter sections, which are all pulse jet fabric filters. I would assume that the single ESP field is the same size as most ESP.
Of course, and don't forget, Carl's report will be available to download next week, and he goes into much more detail in the report. Okay, I think that's all the questions now, so thank you very much, Carl, and remember our next webinar on the 22nd. Oh, no, one more. Okay, this is the last one. Are the investment costs of ESP higher than fabric filters?
I can refer back to my previous slide here, which gives a summary of the relative costs. As you can see, the costs for an ESP are at least double that of a fabric filter in terms of capital cost, operating cost and maintenance cost.
Okay, now we are going to wrap up. The next webinar on the 22nd of May will be on circulating fluidized bed combustion. We hope you'll tune in then. Thank you. Bye-bye.